All right, let's jump to another problem here. Here's another problem. I don't think you'll have too much problem with this, but I just want to go through it for those that maybe struggle a little bit with the conversions or maybe using the kinematic equations. Again, they're asking for the force exerted by a catcher. They give you the force exerted by the catcher, and they're asking for the mass of a ball. Well, obviously, if you know a force and they're asking for mass, you'd like to find, you also need to know acceleration, because we've got our equation here, which is the thing that relates force and mass, but we need the acceleration. And the information we've been given over here, the speed of a pitch that comes to rest in 0.15 meters, will allow us to find the acceleration by using our kinematic equations. So I know my delta x is 0.15 meters. I know my initial velocity at time 0 is 92 miles per hour, but I've got to convert that into meters per second because I've got units of meters here and I've got newtons over here that have meters buried in them. A newton is a kilogram meter per second squared. So that again is a meter. I can't work with hours and miles because I've got seconds and meters in a newton. So, and then I want to find my acceleration. And I know if he brings it to rest, the final velocity, v, is also 0. So I've got delta x, I've got v, I've got v0, and I've got a. Which one of my equations, of the 4 equations that you know that we derived kinematically back in chapter or unit 3, can you use? They don't have time in this problem. They don't ask for time. They don't give us time. So it's that last equation that looks like this. We're going to solve that for acceleration, and then we're going to substitute it into this equation up here, and then we'll be able to figure out what the mass of the baseball is. I'm just going to rearrange this for acceleration to delta x. And I will do my conversion here, miles per hour. I happen to know that in 1 mile, there are 1,609 meters, and in an hour, there are 3,600 seconds. So that gives me, in meters per second, 41.1. So I come down here and I say my final velocity is 0. Subtract 41.1 squared, 2 times 0.15. It's going to be a pretty big acceleration. So let's square the numerator, divide by 0.3, negative, because the acceleration is in the opposite direction of the ball's motion, and the ball's motion was positive. Meters per second squared. This is 803 newtons here. So this is going to be 803 over 563. Oops, I got to rearrange, don't I? For mass equals F over A. So 803 over 5,636. $142 grams or 0.142 kilograms. Okay, see if that works. No, I used too many sig figs. All right, so that's a typical problem that combines kinematics and Newton's second law, which is the F equals ma, or the A equals F over m. Let's go to a new one. Okay, so in this one, this is a vexing problem, usually, for you guys when you first do it. But you'll see it's not too difficult if you approach it the right way, and I tried to give you that video before the weekend to help you a little bit with it. We've got 3 boxes. They give us the mass of each individual box. and we know the magnitude of the push force on the one box on the left, I guess it's called box 1, is 7.5 newtons. We want to know the magnitude of the contact forces between these two boxes and then between these two boxes. Okay? Typical Newton's third law problem, but you have to use what you know about unbalanced forces and force diagrams to solve it. So the first part of the problem, just like I mentioned in the screencast that preceded this particular one, is to take these three boxes as if they were one big box, because when you push three boxes that are resting on a floor, you know they're all going to move as one. Okay? Now notice this problem doesn't mention friction. We haven't learned about friction yet. We have to assume this floor is frictionless because there's nothing referring to friction in the problem. So there's no way for us to know what it would be if they don't tell us anything about it. So we ignore friction, and we've got an unbalanced force in the x direction. If I drew a force diagram of all three boxes together, I would have the force of the earth on the boxes, I would have the force of the ground on the boxes, which are equal, and then I'd have the unbalanced force, which would be this big push force, I'll say the push on the box of 7.5 newtons. Okay, so the unbalanced force, the acceleration of the boxes as a group, is just going to be the total mass of the boxes being divided into the unbalanced force, which is 7.5 newtons. If I sum those three together, I get 8.1 plus 1.3 is 9.4 kilograms. So my acceleration is going to be 0.80 meters per second per second. That's important to be able to answer the contact force question, and here's why. Once I know that, now I can go back, I'll write that over here. I can go back and I can look at each box individually, and I can analyze the forces on each box separately. So I'm going to draw a force diagram of box number 1. And I'm not going to worry about the up and down forces because I know those offset each other. The normal force of the floor, the support force, is equal and opposite to the Earth's pull downward. So the only forces I'm going to worry about are in the x direction. There's a 7.5 Newton force acting this way on box 1. Remember, this is box 1. And there is a contact force with box 2 right here that is opposing that. So I've got some unknown, I'll call it force of box 2 on 1 in this direction. And because box 1 is accelerating, I know they're unbalanced. Okay? I know 7.5 must be less than 2.1 because the box is accelerating to the right. So here's what I'm going to do. Let me go to another page here. I know acceleration equals the unbalanced force divided by mass. The unbalanced force in this case is the difference between the 7.5 newtons here and F of 2 on 1. So the unbalanced force is 7.5 minus F of 2 on 1. The mass that I want to put into this formula is going to be just the mass of box 1, 1.3 kilograms. So that's 1.3 kilograms. And I know the acceleration of box 1 is the same as the acceleration of all the boxes together. They move as a group. That's 0.8. So the only thing I don't know in this formula is this equation is F of 2 on 1. Solving for F of 2 on 1, I have 7.5 minus 1.3 times 0.8. All I did was I moved the 1.3, I multiplied both sides by 1.3, and then I subtracted that over to this side and added F2(1) to the other side. And so this is going to tell me the contact force between box 2 and 1 is this is 1.04, by the way. So this comes out to be 6.46 or 6.5 newtons. I'm sure they wanted to 2 sig figs. The contact force between box 2 and 1, this is where Newton's third law comes in. Oops. Whatever force box 1 is pushing on box 2, or I'm sorry, the other way around. This was box 2 on 1. Whatever force box 2 is pushing on box 1, I know that the third law paired to that is 1 on 2. So it's 6.5 newtons is the contact force either way. So I'm going to go ahead and type that in and see how we did it. Okay. Oh, I guess they wanted 3. I wasn't paying attention. Okay, the magnitude of the contact forces between box 2 and 3. Well, now I only need to do one more force diagram, and I can use either box 2 or box 3 to draw a force diagram. And I'm going to go ahead and choose box 3 because it's a little bit simpler. There's only one horizontal force acting on box 3, and that's the force of box 2 on box 3. That's the unbalanced force acting on 3 in the x direction. So coming to a clean page here, this is box number 3 here. I'm not going to, again, draw my gravitational force or my support force from the floor. Those are going to cancel each other out. So box 3 only has the force of box 2 acting on it. That is the unbalanced force. So coming to my equation again, unbalanced over mass. This will be the mass of box 3. Acceleration of box 3 is the same as the acceleration of the system, which the mass of box 3 is 4.9 kilograms. So this is going to be 4.9 kilograms in the denominator, 0.8 meters per second per second. It's moving at exactly the same rate as all the other boxes are. So 0.8 times 4.9 is 39.2. So the unbalanced force is 39.2 newtons, and that is this force right here is the unbalanced force in box 3. So 39.2 should be my answer there. I do not feel good about that because I did something wrong. It should be 3.92. That makes a lot more sense. 3.92.